Hello and welcome back to a new video, real-time rendering here on the Lötwig Fusel channel. In today's video we're gonna talk about geometry, so all the data that's making up the geometry, looking of our rendering, our game, our level, our movie, whatever we want to real-time render. So in general, if we take that picture here as an example, right, like the shape of this hallway is defined by geometry, of this hatch here in the wall, the shape of the, like, so I think it's speakers there in the wall, like the ventils. It's actually Jill herself. She's also defined by geometry. The weapon, the gun she's carrying is also all defined by geometry, and everything that's kind of like building up your scene is defined as geometry. This doesn't conclude like colors, like all these colors, water effects. These are not in general geometries. They are special things. We just talk about the geometry, but I'm gonna get to that, what this really is, in a second after the intro. Alright, so real-time rendering, I think it's actually part 3, or is it 2? I'm not quite sure. I think it's 2 or 3, right? Geometry. Haven't done a video in a while. So let's talk about geometry today. So what we're going to talk about is what is actually geometry. I've just give you a quick information on that in the intro. Then we're going to talk about how we render geometries and why we only use points, lines, and triangles. And after that, we're going to talk a bit about the difference between the geometry and 3D models and what 3D models actually are. And we're also going to talk a bit about the workflow on how to author geometry, how to author 3D models. And then we're going to talk about the architecture, how I plan to implement this in RTR. A big information here, I haven't implemented this yet, so this is just going to be an overview on how I want to implement this. It might probably change a bit in the actual implementation, but we're going to see the theory, and then we're going to have some coding videos maybe, or an explanation video where I go over the code base, so that we can actually see how it changed during what I worked out from the workflow to an architecture and what then it finally has become. Alright, so let's start by talking about geometry, so describing your worlds with bits and bytes. Now, what is geometry? Well, geometry in general is a computer-based description of the shape of objects, and as I already told you, for example, a character is defined out of geometry. So it is some information stored in a computer, in a file, right? Could be any file. There are multiple files for geometries, file formats, and it's basically describing how this character shall look. And what we need to do as a rendering system, as a renderer, as a rendering engineer, we need to be able to read these informations, transform them, and bring them into an image. And one step of bringing these geometry models or making visuals like that is actually taking a look at the geometry. So the geometry is kind of like the shape, not the color. So if we really take a look at the geometry, it's more like this giraffe that I have taken here. You can see that this giraffe is just built out of lines, and this is an example on how geometry for a giraffe can look like. It's just a definition on how the shape of the giraffe is based on like this wireframe that's kind of like defining points and lines between these points to kind of like build the surface on how the giraffe shall look. And that's the idea, right? Geometry is a computer-based description of the shape of objects. So the concept is quite simple. Data defining how something shall look in terms of the shape. That's geometry. Now, in general, a bit of more mathematical representations. Geometries are kind of like points. I forgot the lines here. Points, lines, and surfaces in 3D space, right? For example, a pyramid could be defined of multiple points. These points can be connected with lines, and connecting 3 points together, for example, can give you a surface, like the surface ABC here on the pyramid. So, yeah, kind of like that's the idea, right? You have a 3D space, you have some points, you have lines, and these are kind of like defining a surface. How this later on gonna look like in the on the GPU side, we might want to talk about that. GPUs are always working with triangles. I might make a follow-up video on that, which is going to go into a bit of more of detail on how rendering APIs like DirectX handle these with like vertices and indices. This is something that we might want to do. I'm not quite sure if I want to really go that deep because I've already done this in the DirectX tutorial series. So, for example, if I want to have like a whole idea on how the whole geometry workflow on the GPU works, I might point you currently to the DirectX series. I might recycle that information in this tutorial series as well. I'm not quite sure of that, but we probably might want to do that, but we're going to see what I'm going to do in the future. All right, so now after we have defined this geometry information, we need a way to render these geometry informations on the screen. So how do we render geometry? Now we start with the geometry information, kind of like this wireframe that defines the shape of an object. We need to split this geometry information into primitives like points, lines, or triangles. We have already done that because they have already been authored like that. So we have them already in a format that we can read, like for example, points, lines, or triangles. Then after we have like this information, we need to transform these primitives to display space because what we have is we have a two-dimensional screen, a two-dimensional computer monitor, and we need a way to bring three-dimensional shapes into a two-dimensional space. So from a three-dimensional space, we project them, this is how you call it, into display space. This is also something that we might talk a bit more about in the future when we actually talk on how to render it on the GPU, but that's not the scope of this video today. Today's video is just a bit of general information about geometry, right? This is like the idea, right? You have like this three-dimensional representation that represents like geometry in a three-dimensional space, and you need to project this into the display space. This is still a three-dimensional space, but it's going to be different. I definitely should do a video on that, but that's going to be in a separate video. So we transform them into display space so that they kind of like line up on our monitor, on our computer monitor. And after that, on step 3, we need to determine which pixels are included in the geometry. So for example, if we have a point, we need to convert that point into like a pixel, which pixel is the point actually kind of like covering. Same goes for lines. We have 2 points that define a line. We need to know which pixels are kind of like touching the line or are like covered by the line. For example, the same thing goes for triangles. If we have a triangle, we need to see which pixels are included in the triangle. And this is a step called rasterization. This is a step that GPU can do. Actually, the rasterization is a fixed function but configurable hardware in the GPU. So this is not programmable, as you can only configure it. And the GPU is just built like has a dedicated silicon just built for converting triangles into pixels, and that's why we also need the GPU, because the GPU can do that fast. If like these rasterized engines or raster operations, I'm not quite sure how the terminology is there, but they can do that fast, right? The GPU can determine the pixels fast, and it's good. And we then basically know that these pixels, and step 4 then to render the geometry is finding the right color for the pixels. So each pixel needs to have a certain color so that we can display it on the screen. And this is something called shading. Shading is a way more advanced topic than geometry, and it's not related to geometry, but this is kind of like the whole flow that we need to do to go from geometry information to a pixelated image of the actual geometry displayed on the screen. So right, these steps are basically required to go from a wireframe information on a computer like that to a full figure rendering like that character here. This now seems quite simple, but it's definitely not simple. This is because there are so many things involved, especially when we are getting to shading. We have so many options to do shadings in multiple passes, and we definitely need multiple passes with like lighting, deferred rendering, and shadow passes, ray tracing, and can like put everything of the knowledge of that amazing features that make your image look good. They mainly all involve writing different shading models. While like something like projection, rasterization, and the initial geometry information, what we are covering like in this video, we just mainly cover the step between 1 and 2 actually. Actually, what we are talking today about is something between 1 and 2 and a bit of information about the whole toolchain here. And it's like a small part, but it's also good because we can start small and we can understand how that works, and then we can go bigger and later on are ready to do like full shading, which is quite involved to do it correctly and physical based and correct and looking nice. But yeah, so that's like the whole idea, right? We start with some geometry information. We are splitting this into points, lines, and triangles. Should already be in that format. We need to transform this so that we can display it on the screen. We need to rasterize it so that we know which pixels are affected, and when we need to compute the pixels themselves. And well, we have it rendered geometry. Now I have a bit of information here again for that. So this is now building up to the point where we can like discuss why we are only rendering points, lines, and triangles. Now, what is actually required to render points? Points are actually quite simple. We need to convert a point to the pixel index, right? We have like this initial point, and we need to determine which pixel index is the point currently located. Now, in general, points on rendering, they are in something called normalized device coordinates. This is basically a coordinate system where the center has the coordinate 0, 0. A pixel up here has the coordinate of y1 and x0. A pixel here is a y of 0 and a x of 1. A pixel up here has coordinates of y and x of 1, while one down here on the left has -1 and -1. So you have like the origin in the center. You go always from -1 to 1, from 1 to -1, depending on how your computer, your APIs work. And you kind of like have these normalized coordinates, normalized device coordinates, and you basically define your points within these normalized device coordinates. And after that, the mapping is performed by the GPU to basically indicate, all right, I have a point with these normalized device coordinates. I'm going to compute what pixel index that is. And then it basically runs the shading for that coordinate that the GPU has determined during rasterization, because rasterization, normalized device coordinates, go in there, it's going to be rasterized to a pixel index, and this pixel is then fed into the engine of the GPU that does shading. But when we are getting to the step where we're actually going to touch the GPU with our projects, we're going to have a full involved video on how the GPU actually works with all of the subsystems and the modeling, rendering pipelines, different rendering pipelines of the GPU. And yeah, so that we can like know what's actually going on there. So points, really simple. You have a point, you just transform it into a different coordinate space, you are done. Right, and with transforming from a coordinate space, I mean from normalized device coordinates to actual pixel index, because these are two spaces that we can transform between. Lines are also not very complicated. They are a bit more involved because they require interpolation, and they also require something like how fine do I need to interpolate, and some involved steps there. But in general, like a line is really simple. You have a starting point, you have an end point, you connect them together, you get the line, you need to check which pixels are lying on that line, and you draw the line. Now, line drawing is a bit more complicated because you can now actually start arguing, the same like with the points here. You can see that I have made a binary decision here with the points, but you could also argue and say, all right, these pixels should also be affected by the point, but that's something that's then going to be advanced, and we would then also render points differently by actually not rendering points, but rendering different primitives that touch these pixels, and using something like conservative rasterizing, and use some math to actually compute how to render points exactly how we would like, but that's also too involved for today. Same here with the line, right? I'm just having a simple example just to show this to you on a concept. If we are getting to the GPU, we can talk about magic stuff like that and how to actually do this. But line, very simple. Connect these two points, have a line, color each pixel that falls on that line using linear interpolation. All right, so now stepping up from the line to a triangle, or better to say from a primitive of order 2 to a primitive of order 3, because like a triangle had 3 points, order 3. The line has 2 points, so it's order 2. And the point just have 1 point, so it's order 1. Order 1, very simple, no interpolation required. Order 2, linear interpolation. Order 3, linear interpolation. I don't know, is it a term? I think it is actually a thing, but it's the kind of like an interpolation that requires 3 coordinates, and kind of like, yeah, it's like defined by a distance of each of these, distance on each of these points. So it's kind of like a 3-point interpolation. It's actually called the barycentric coordinate system. If you are in a triangle, it's a special coordinate system that you kind of like need to require to define each point inside of a triangle. And yeah, but in general, like, we don't care how this works. We just give like the GPU 3 points, and the GPU with these 3 points can rasterize all these pixels out of there. Quite simply. However, in general, like, it's way more advanced, right? If you have a point, it's quite simple. A line is a bit more involved. In the triangle, you can already see that we have way more pixels and a way more complex algorithm that needs to run to actually find out which pixel are affected by the triangle itself. So, yeah, it's a bit more involved. It's way more involved than like points, and also way more involved than lines, but it's still like a capable thing to do. However, this was actually an issue quite a while back, but it the GPU is designed for that, right? The GPU has been has a dedicated hardware system that is just built, dedicated silicon to just rasterize triangles. GPU is designed to do that. We don't need to know how it works. We just need to know that what it does, right? You give a 3-point, it rasterizes pixels for us. It is configurable. You can do magic with that, like conservative rasterizing, which would also color in this example this pixel, this pixel, this pixel, this pixel, this pixel, and this pixel. Again, here I've just done some example here, just have something to show here actually. And yeah, way more advanced than like order of 1 or order of 2, but still doable. Now, how would we render quads? Now, quads would be a system of order 4. However, do we actually need quads? Well, actually, we don't need quads, right? We also need a point to stop. If we would have a dedicated hardware system to rasterize quads and then a dedicated hardware system to rasterize, like, what is it? Like order of 4. Let's talk about orders. That's easier. Like order of 4, you need a dedicated hardware system for order of 4. You need a dedicated hardware system to order of 5. And if you have a big character, you know how many orders there might be of polygons inside of that character to actually render it. Maybe order 16 or something like that. However, this is not required. We do not need hardware to handle that high order because every closed loop polygon can be converted into triangles. Right? Every 3D modeling program, no matter on which order of polygons it works on, you always have an option to triangulate your meshes. And if you have closed loop geometry, so geometry that is closed, that is not like broken up and has some holes in it, if you have like closed geometry polygons, it can be always converted to a triangle. The most simple one is find a center point in like a polygon and then connect it to each of the vertices. These are like the points in the polygon. If you have like order of 5, make one in the center of all of them and always connect them to the other points that are defining the geometry, and you have a whole lot of triangles. And there are also different algorithms that find the right way of triangulate something. You can actually use something like voxel meshes that are way advanced. You can triangulate all of these, and every 3D modeling software that's out there is going to support triangulation. So what you can always do, and you're always going to do for the game industry and interactive industries, you're going to always transform this into triangles because the GPU can handle triangles natively. There's no need to implement something custom on the GPU. Side note, Epic Games actually did implement their own rasterizer on the GPU because in their case it was faster because they have like all of these triangles that are just 1 pixel big, and if you have 1 pixel big of triangles, they are probably then emitting points. Not quite sure how they're really doing it, but this is at least how I would implement this. And yeah, they have written their own rasterizer, but they have just written this because like it performed better. But again, the industry is going to adapt also to the Unreal Engine system, and you can bet that NVIDIA is working with Epic Games and also AMD and also Intel, that they are all working with Epic Games to also bring rasterizers that bring performance on 1 pixel triangles. But yeah, that's just a side note, right? So every quad can be converted into triangles. A quad is simple, just draw a line in between. You have 2 triangles that you can use. And you're going to see later on that this is not going to be that much more data usage that we even have if we're just dividing these. It's like, let's see, 3, 6, 2 more 16 or 32-bit values. Just to talk this a bit on numbers here, but that's going to come in the future. So, right, rendering quads, we don't need this. We are going to stop there. Triangles is going to be the highest order that we're going to get to on the GPU, and we don't need more. That's a big, important takeaway here. Now, the biggest question is, where does our geometry come from? Because if we are implementing a system that handles geometry in our C++ code base, we need to know where the geometry is coming from to implement the system and design the system right. Now, we have actually 3 or I potentially, just by thinking about geometry, I have like 3 sources where geometry can come from. Now, the most common source of geometry where it's going to come from is as a 3D model from a content creation tool. For example, if you're modeling a 3D model in Blender, 3ds Max, Maya, Houdini, or any other 3D modeling software out there, you are going to design that in that software, you're going to edit that, you're going to create nodes in Houdini, you're going to maybe model something in Blender with like sculpting, for example. But at some point you are done and this model or this modeling tool is going to output you a file, for example, an FBX file or an OBJ file that is going to contain the information on how that object looks. And yeah, this is one source of it. It's a 3D model that's coming from a content creation tool. It's an FBX. You import this into your engine, and the engine loads the FBX file and can render it on the screen. You can tweak it, and it's looking nice, or it should hopefully look nice if you implemented this correctly and you are good at doing such things. This is one and the most common one that's going to happen. However, it's not the only one that can happen. For example, what there could also be is pre-computed generated geometry. So it's not originating from a content creation tool. A content creation tool is very classic. You design 3D models like buildings, characters. They are kind of like static, even though characters are not static. But yeah, they might have animations and they might split into multiple objects. But the geometry itself is kind of static. It's created in a tool. It's only going to change if you're going to go in that tool, change the object, re-export this, re-import this into an engine. And that's like one big thing. However, what could also happen is that something in the engine is going to be generated. For example, most common example is terrain. If you are building a level that is outdoor, it is most certainly going to contain the terrain. A terrain is like the ground where the people walk on, like the grass, the rocks, the hills, the mountains. It's like all defined by terrain, like kind of like the surface of your outer world, of your outer scene. And this terrain is normally generated in the engine. So if you are going into a game engine, you create a new terrain, you're going to get a flat terrain and some tools where you can like sculpt the terrain, raise mountains, create hills, valleys, like rivers. You can like do everything. You can like model it from how it looks. You can paint it so that it has textures on it. And then you have like your whole terrain. And normally in an engine editor, this is all generated live because you can live change that and it's all like computed on the fly. However, if you're shipping your game, there's no need to put like this extra amount of work into that to actually render the terrain live on a GPU. So on an editor, this might be feasible. You kind of like give it the most basic information how terrain looks, like it's a flat surface, and then on the GPU you apply the offsets so that the terrain is kind of like drawn from like a texture or something like that. There are multiple ways of rendering terrains. And this is something that you might not want to do in production, because in production, the terrain has been created and you want to make it run on the lowest hardware possible. So an easy way to do is to actually export this terrain geometry as a static mesh, like it would come from a content creation tool. This is an optimization that we can apply in real-time rendering for production to be faster in production. And we can also apply this in our editor. So if somebody is finished with the terrain, he kind of like says, all right, finish terrain editing, then a progress bar appears, the terrain is like regenerated, exported, and then it can also again run far faster in the editor. This is also something that we need to take into account. Our geometry in the system needs to be able to handle such geometry. It's not only that this could be terrain, this could be, for example, also ornaments. I recently saw this like somebody doing on YouTube. They have like a flat surface and they have like a texture that is like defining some ornaments for like stones or like bricks and something like that. They define like the ornaments as a texture, and then the ornaments are like kind of like applied automatically, which is nice because you can just author them in any tool, and you can apply the ornament to like any other 3D object that might be out there, and you kind of like feed it in a 3D object, and you're gonna generate an ornament on top of that, do some transforming and things like that. Also a handy tool to have in your game engine. Might be something that we're not going to implement straight away, but something that you could do just out of proving that it works. And yeah, it's going to be useful because you can also like procedural generate them later, and also move this a bit about on the live generated geometry. But yeah, also a thing that could happen, right? And also a thing that needs to be capable. Your system needs to be capable to handling such things that are not generated, that are not coming from a FBX or OBJ model file. They're coming from some other kind of like metadata to be computed and then shipped with the game. Then also quite related to what I've now told you about the generated geometry is the live generated geometry. The main difference between pre-computed and live generated geometry is the point where it's going to be computed. The pre-computed generated geometry is something like, it's procedural generated in the editor or during build steps of your game, and then it's shipped as a static mesh, similar to your FBX. At the end, if you have pre-generated geometry and geometry from a 3D modeling tool, at the end, when it's at the player, for example, it is the same. It's looking the same. There's no difference between these two. But on your editor, it is a difference. On your editor, you have at the one point the actual static mesh that's important. On the other point, some dynamic data that you can tweak in the editor. On the other hand, the live generated geometry is something that's never going to be hard shipped. This is always something that's generated at runtime. For example, like if you played like something like Tomb Raider or Mirror's Edge, you can like ropes. You can like in Mirror's Edge, you can jump, and then you can attach a rope to like a building, and then you can pull yourself up. That rope, for example, needs to be live generated. Some kind of like rope system is like in each engine in there, or can be done with each engine. You have like define a start point and an end point, and you have a rope between these 2 points, and you're gonna apply a texture so that the rope looks nice. It's a very simple system to implement, but you can again as well, if you want to compute something like if you have a rope which has a weight that this rope actually is gonna bend, you can also overdo things like that, but in general, it's a quite simple thing, but it's also something that's not static. It's geometry that needs to be live generated, right? This rope has an end at the start point, but cannot be rendered as a line because it needs texture. So we need an algorithm to take the end at the start point and some diameter for that rope to then actually compute the triangles that the rope is going to cover. So there is something involved in there that you need to actually generate, but this is something that needs to be live generated because these points can change, right? Because there's an attachment point, which might be fixed. However, you don't know where the player is when he attaches himself or herself to that rope, or to that attachment point with the rope. Same thing goes for things like mud or snow, like in Tomb Raider. You have like these between two streaming units of the game. So like one big area of the game, another big area of game, a narrow hallway between two of them, and so that you have, or the game has enough time to actually load that new area, you have some mud where you can only slowly progress through that, and instead of you just being annoyed that you cannot walk fast, you can at least see your footsteps being like drawn into the mud. Kind of like, and it's also a runtime feature, right? You have like this mud puddle, and everywhere where you place your foot, it's going to kind of like carve out where your foot is going to go. It's actually quite a nice article in some of these GPU Pro books that actually explain the math and the rendering behind these, which we might going to go into that when we are at writing such rendering goodies, which is quite some, I would say, years away. I don't know. I don't hope that it's going to really take years, but it's probably going to take some, at least 1 or 2 years until we get to something nice as that, because this is involved rendering, right? This is all like examples of live generated geometry. Same with hair, for example, TraceFX, which is something AMD has developed. It's completely open source. There are plenty of articles on how to do it. You don't even need to use like their TraceFX and their code base. You can write your own implementation and change it so how you like it. It's also like how hair works. You have control points that are kind of like on the head of the character, and from these control points you kind of like grow hair and apply physics simulation to the hair, adding some constraints. For example, if the character has like the hair bound together, you can apply some constraints where the hair is connected, and you can feed this through your physics and have nicely runtime generated hair. Also an example for live generated geometry. Now, geometry is a very big thing, right? This is not ending here. These are just a few examples on what you can do and how you can do this, at least a bit of theory here. However, this is just some input for you so that you know that we are dealing with quite a complex system, right? It's not just, hey, use asimp to import an FBX and directly use it from there. No, geometry is involved. And that's why we need to really overthink this. Many people, they just think, all right, geometry is simple, just one CPP file, not some thoughts into that system. It's easy. But as soon as you're going to implement things like that, and I want to build that toolbox that can do all of that for real-time rendering, because we want to do that later on. I want to later on have an easy and good usable framework for building things like that, not some convoluted piece of shit code that we cannot work with. So now, especially these like basic systems like resource management, geometry management, file management, these needs to be all written rock solid. And I hope I can do that. It's always like, if I take a look at my old implementations, I think, oh, they are shit. But back then I thought, all right, this is now the best one I've ever gonna write, and it's gonna be so 100% satisfying. That's always what you're gonna get, but just at least need to have the big picture. What do you want to do? And I want to be able to do these 3 things, which is why I developed the workflow out of that. Now, how does the geometry workflow of our engine should look like? Step 1, 3D modeling tool exports a FBX or an OBJ or any other file that SM can read. So 3D modeling tool, Blender, 3ds Max, Houdini, whatever, gives you a 3D model as an export. This 3D model export needs to be able to be handled by a renderer live model import. This should be a piece of code in our software that can take an FBX file from disk and convert this into some optimized binary intermediate. This is the data the GPU is later on going to read. This is the data that's going to be directly fed to the GPU, but that's the workflow that we need. So live import, and with live input, I mean the engine starts, the renderer starts. I not want to talk about engines here because we are doing rendering and not a game engine, but let's face it, we are building a module for a game engine, so why not call it engine? Even through that, I might recycle real-time rendering completely and integrate this into a game engine later on as well. Or also build these side by side. We're gonna see where this ends, if this is gonna grow bigger. But if I write a rock solid renderer, why should I write it twice and then again for a game engine that I might do on YouTube? So yeah, these 2 projects might get together into one. But that's not the point here. So the point is a 3D modeling tool, FBX export. We're gonna take this live on engine startup from the disk, read it into that, and convert it into an optimized binary intermediate that later on our actual renderer, our actual rendering pipeline can understand and directly render on the GPU. Right? This is like our development path. We have something exported from a tool. We're going to live import this into the engine so that we have some optimized data that the GPU can render that can then be displayed on the screen. Right? This is our workflow from the GPU point of view in development. However, what we also want to have is we also want to be able to generate something that can be later on reused on shipping. So we're going to have a renderer tooling application. It's maybe some code or some application. And that tooling application shall be able to actually take that FBX and directly output a optimized binary intermediate. And now you can see like, hey, it's kind of like the same flow. Yes, but that one is a live flow. That's kind of like the live flow that is going to go on development. We load the FBX, we convert it. It's an optimized binary. It goes through the renderer. But then if we are going to build our game, the FBX is going to be taken, gonna go through our tooling application, and the tooling application is spill out an optimized binary intermediate so that at runtime we can take that binary optimized intermediate directly from disk and directly fed it into the renderer, leaving both of these green boxes out. And each of these green boxes are parts of our engine, of our renderer, subsystems of our renderer. And the fewer boxes that we're gonna have, the faster is our code. So if we are on development, yeah, we use the live import and the renderer, 2 systems. If we are on a shipping configuration, we're going to deploy it. We're just going to use the renderer because we directly are supplied with the optimized binary intermediates. The tooling application, it's run on build once. So we are kind of like offloading the cost from a cost that needs to be done on a per startup to a cost on a per build. Very simple flow here. And yeah, we also gonna, of course, need some metadata here. Why did I put in metadata here? Yeah, because it's a different workflow. All right, I don't even know my own diagram. All right, now the runtime or the pre-computer generated geometry also needs to be at some time produce a optimized binary. So for example, this metadata, for example, for ornaments or terrain. The terrain is just going to be built on top of metadata. Some terrain metadata, you have terrain metadata. It's fed into a tooling application. It's going to be, of course, a different one than the tooling application reading the FBX. It's going to be a tooling application like terrain build, while the FBX importer is kind of like a model build and terrain build, 2 different tools, both of them producing the same kind of like output binary intermediate that can be consumed by the renderer, right? 2 different input formats, same output format that can be reused and recycled so that we have a uniform way of actually displaying data. Now we also have another code path on our workflow. We can have some live metadata. So for example, like this rope metadata, the mud metadata, the hair metadata that is going to go into some renderer live code that also produces optimized binary intermediates that are fed into the renderer. And yeah, you can see that like everything revolves around an optimized binary intermediate. And this is like the whole idea here. The optimized binary intermediate needs to be universal. It needs to be universal because we want to have one workflow on the GPU. We do not want to implement 5 times a similar workflow on the GPU. The idea is that geometry always gets to the GPU in the same way. How the GPU then handles it, for example, how the rendering is invoked, with which shaders and which pipelines, that might be something different. But the path to the GPU should be the same for each geometry, no matter where it's coming from. If it's live generated by some live code, if it's created by a tooling application or by a live importer. That shouldn't matter. The workflow should be straight away into the renderer. And yeah, that's our workflow. Now we need to define some architecture out of that. So how I'm gonna do that architecture, right? Simple, flexible, and fast. That's the whole point there. It should be simple to understand, flexible for handling multiple data, and it should also be fast. And that's what I hope that we're gonna get to. I haven't written that actual code, so I can't promise it's gonna be there, but we're gonna write it as best as we can. All right, so our whole concept of the architecture and RTR is going to be defined by geometry generators. Now, a geometry generator, the green box here in the middle, works on some input data and produces some output data using a configuration. So the general idea is some input data gets transformed by the generator by some output data, which, again, output data, input data, they should be the same format, data format. They might have some different properties and a different layout, but the general format should be the same, right? Being built on the same interface, kind of like if you're talking a programming style language here. So that in theory, you can actually run some data through 2 generators. So input format A goes through generator A, produces output data format B. Output data format B okay, I should have used B here as well and then use C here. Yeah, I don't know. Right, the slide is a bit convoluted, but yeah. The idea is like data format A goes through generator 1, produces output data format B. Output data format B goes through generator 2, produces output data format C, which then might be consumed by the renderer. And each generator can also have some configuration that's going to be used to kind of like parameterize the generator independent of the input data. So input data can stay the same, but the generator has different configurations. For example, like on something like creating ornaments, the ornament is kind of like defined maybe by some height map, a height map texture, which defines how big it or how high it should be raised. And then your configuration would be kind of like an overall height, where you can say like, all right, the overall height of actually offsetting the geometry that's affected is like 0.2 or 0.5 to give that some additional input parameters for the generator to actually produce geometry, which is also something that should be possible. Right? This is all going to resolve around some descriptors. These descriptors are going to be the information how everything is built up. We're going to have some mesh description, which has like some source data format and some target data format that we want to reach. Like source is describing like how it looks. So what's the type, for example, a model file, and then some custom data, for example, the path to the FBX. You have some target format that's going to be initially null because the mesh hasn't been transformed. Intermediate also going to be null. You have some generator information, just hard coded to 8 here because 8 generator should probably be enough at the most of what should happen. And then kind of like what happens is that these generators are walked. So you kind of like start with the first generator, it produces from source to target. If you are there, it's done. The destination is stored in target. If you have another generator left there, the target is copied to intermediate and you work from intermediate to the next target. So that source is always going to be at the initial value. So, for example, if the GPU no longer needs a resource and we optimize it away by evicting it from the GPU, so that's no longer preset in the GPU memory, and it might also be get evicted from the CPU, so that we still have like the initial original description, which might have like something like the path to the FBX file and the type, so that we can always regenerate this and reuse these mesh descriptors that are just loaded once. Right, additionally, maybe some state descriptions so that we have some state of the generators. The general idea is that the generators are itself stateless. So the generator itself, it's just like an interface, and the instance is created once. And rather than really working on its members. The generator operates on like a generator state, so that it kind of like maintains stateless, and you can also like have multiple threads operating on the same generator, because the generator itself is stateless. They all have their same states, and some nifty optimizations there so that generators run as fast as they should do. Generator itself, like generator info, build up out of a generator pointer and some arguments for the generator. Geometry itself, already told you that, like a type and some custom data attached to it, and the generator state description kind of like bound to a generator, and some generator state. So generator state, it's a bit redundant. I cannot guarantee that I'm going to implement this one by one, but at least this is like my goal to implement this, and more or less it's going to be that architecture plus some interfaces plus some static code that kind of like drives these interfaces and provides a async multi-threadable framework for that. Because we are writing in renderer with DirectX 12, so everything needs to be async or asyncable and thread safe. How the work is then actually going to be handled, we're going to see. We're probably going to write an async interface that's used in a sync way, and at some point we might switch to multi-threads, but that's a big point. However, having multi-thread in mind when designing your systems, especially on modern game engine design, renderer design, it's a thing, because we are optimizing on the CPU, right? We need to get data fast to the GPU, because that's where we need to do our work. If we render this, we want to have like 144 FPS. That's the thing, right? This is all a bit convoluted, but it's a big topic. We are handling a hell of a lot of data. I already told you that. That's a massive amount of data that we need to have as a throughput, and we need to be flexible with that, fast and extensible, and also simple. And I think that's simple. We have a configuration, a generator, and data formats. And here we just have 4 descriptors. If we can handle this with just these little bit of information, it's quite a simple but effective and powerful system. And that's what I hope, and that's what I'm going to implement. Have fun. Videos will come when they are ready. This is not a regular video series, especially now, because I need to do a hell of a lot of coding. So have fun learning, have fun playing around with C++, have fun buying yourself books, have fun reading these books, have fun exploring programming, do projects that you like, write yourself some console games in the meantime while you are learning 3D rendering, or some simple 2D games. There's so much more to do, so much more things in programming. So enjoy it, be yourself, and don't let somebody else stop you coding. So thank you for watching. See you in the next video. If you liked, please like the video, of course, and subscribe. So thank you for that, and have a nice time. Until next time, bye.